Right. So we'll start with discussion on the dynamic characteristics. So into this segment, we have to understand first the response of the measurement system. So if you recall in the earlier discussion, what we told is the measurement system is consisting of number of elements into it. Say for example, primary sensing element, then the signals will be passed on to the variable conversion element. From that it will go to variable manipulation element, then it will go to the data transmission element, and then display. Let us say these are the functional blocks in your measurement system, right? So when the instrument or the measurement system is exposed to the system of which the entities to be measured, so let us say this is the input, the response of the system is going to differ because the primary sensing element is going to come in contact with the system or the entity under measurement. Am I audible to you all? Please let me know. Am I audible?
Yes, sir, you are audible.
Right. So so much time you are taking for saying yes? Okay. So the primary sensing element will come in contact with the system of which the entity is under measurement. So the signals will be captured by the primary sensing element, and then it will have the very proportionate signal being given. You may take an example of, say, a thermometer, a mercury and glass thermometer that you have used somewhere in your earlier standard, say 12th standard experimentation or 11th standard experimentation. Or we know the doctor's thermometer at home. So what is the procedure for measurement? Suppose we want to take the temperature of a patient. We apply the thermometer and then we wait certain time, say 1 minute, 2 minutes, or so on. Even if you are using the electronic thermometers in your household applications, you find we have to wait till it gives some sound, beep or buzzer sound it gives, and then at that point of time the signal are, say, given as a confirmed display of what is the entity in the system. So with this say example, what you can understand is that due to the system or the instrument, it cannot give immediately the final value or final status of its state. We have just now discussed the example of the thermometer. So it is because of the input when I am giving, say for example, the patient, the thermometer is applied to the patient body. Say I have given the, say at this time, say for 0 instance of application, I am exposing this as an input. Say input is given. Now I am applying this continuous input. Say, or you take example of dipping the thermometer into the water bath at some elevated temperature. But the configuration of this instrument or the measurement device having the primary sensing element, VC, VME, and so on, all elements will have its own response time. So it will say take the measurement and then it will finally show some value here. So this can be the output. If I'm going to show that with some different color here, say the input is given and this is the output shown. So it will take some time. Now this is your output. So this is the response that is because of the system itself, the characteristics of the components, maybe physical components, maybe functional components into it, and it is going to take some time to show the final value, right? So then it goes through. So this is the stage in which it is going to have the transient state before it finally settles to its the steady position. Right, so it means that in between this, if there is some display, if your digital thermometer is showing some reading, say for example, say 97 Fahrenheit, 98 Fahrenheit, and so on, it is moving on. It is continuously increasing the readout, right? So if that is taken into account, any of the reading shown before it comes to the settled value, that we call as a transient state response of the system, or say the transient reading that is given by the display of your measurement system, right? So some of the measurement systems are made under such condition, very few, right? So in a general way, we have to allow this sufficient time for the instrument or the measurement system to settle to its final state in the condition, right? So then under such condition, the study of the behavior of the system is under the transient state and thus known as a transient response of the measurement system. And many places this may not be of use. Say, take example of the thermometer, temperature measurement of, say, a patient, or we are taking the temperature of a patient. So in this condition, the reading shows, say, from 96 Fahrenheit to, say, the exact value where it settles, giving the beep sound, suppose 101 Fahrenheit. Now, any of the readings shown earlier to this, that it comes the settlement value of 101 Fahrenheit, is of no use, right? So it is not of importance. And many times when we go for the measurement practices, we are intended for having the status measurement at a very stable condition of an input, right? So in many areas of the measurement system, it becomes necessary to study the response of the system under both transient as well as the steady state condition. If I go back, suppose the measurement that is shown as an output here by the thermometer, onward this will be more stable. So then this is a zone A of a measurement response of the system, and this is zone B of the measurement of the system, right? So this, if I call it as a transient state that I had defined here, transient response, say zone A from the figure, and the latter part will be a steady state measurement characteristics of the measurement system, right? So that's what it is saying here. Many of the areas of the measurement system, it becomes necessary to study the response of the system under both transient as well as the steady state condition. It is many places you will find that both measurement become necessary. So take an example of the thermometer again. If the thermometer is going to take the measurement of the temperature of the water, or say some fluid kept at some temperature, and because of the process happening, the heat is emitted, or there is it is exothermic reaction, suppose. So temperature will increase. So in that condition, after the thermometer is settled with the constant input at that particular point of time, onwards it becomes necessary to have a very fair reading of the changes occurring into the system because of the exothermic reaction in this example, right? So then it becomes very important that we should have the measurement of the temperature. Again, coming to this, say for example, this is my first input, then this is a second input, and the response shown by the thermometer to this is, say for example, it is coming here, then again it is say reaching here the steady state value. After that, again it is going to have, so this is one case where there is an input changing with the same time. So then there will be a little change. This may not be directly the step change, but it can be the gradual change. So this depends on the application. But there are many cases where we need to come under the for the measurement of the transient as well as the steady state conditions, right? So in many applications, the transient response of the system, that is where it settled down to its final state condition, is more important than that of the steady state. Opposite to this, there are many situations where we need to take the measurement when it is in the transient state. Now, if you are considering the measurement only and only into the steady state, we have done this in earlier cases, that is called a static characteristic, right? So that is, I can say that this is the static characteristics of so they are the static characteristics that are going to give the, say, response of the measurement system after a very steady state is obtained. So this is what we have studied already. All the properties that we have studied in your experimentation, calibration, and so on, the practical experiment that we have conducted, those were corresponding to the static characteristics of the system. Whereas there are many applications where we need to carry out the measurement only in the zone of a transient response of the system, right? So into this, the transient response of the instrument is on account of the presence of the energy storage elements. So this is very obvious. Say take an example of the thermometer itself. It has got the mercury into the bulb, and that mercury is going to store some energy. That is something called as a loading of a system. that loading is going to make some changes into a primary sensing element, and because of which it has got some kind of say delay in the output of the measurement system, which then very faithful correspond to the input applied. So it may be because of say electrical inductance, capacitance. So these are the elements that are going to be present into your variable conversion element, variable manipulation element, and so on. So definitely it is going to have some kind of time lag, some time between the input is applied and it is going to respond to the true value of the, or approaching to the true value of the input given. So it can be mass. Say in this case it is mass of the mercury that is present into then the fluid and thermal capacitors, etc. These are the say very obvious elements into your physical as well as the functional blocks of the measurement system, right? So then the resultant is the sluggishness that we find, sluggishness of due to account of the similar items that we discussed, like electrical resistance, capacitance, mass, fluid, and say energy absorbing devices like the cantilever or the spring elastic elements into elastic members or mechanical say devices or mechanical systems, or a measurement system consisting of combination of these components. So this sluggishness we need to encounter by taking into account the head of dynamic response. So that is one of the reason of the dynamic response of the system. We try to understand the situation. This is something leading to the dynamic response, and that we must quantify, and we must know how it is going to behave in the dynamic response if some input is given to one of the measurement system. Say on the contrary, we are now discussing the second example where the input is going to change with respect to time. Say for example, again coming back to the example of the thermometer itself, say the standard input that I applied for 1 instance of time, let us say this is time zone 1. Then the second example that I have taken, again I am going to give some input to this, there is some changed input. Please pardon with the figures. Actually I want to show this as a straight line here. So then it can happen in cycles. After say a certain period of time, the input may change. Say for example, for first 1 hour. So take example of your two-wheeler. If you are running with a two-wheeler and you have started from 0, you have say crossed some say 5 kilometers, 10 kilometers of running. Afterwards, you will find that the engine area is going to the gearbox area is going to become more hot because of friction and other things. The oil is going to take the temperature. If you continually operate for another half hour, say if you ride for another half hour, you will find the element is going to become more hot. So it means that if we average out say time 1 hour, 2 hour, 3 hours of operation, you find input goes on increasing. So here also we need to understand this, and if this is happening in a very short period of time, then probably the instrument may not reach to its stable value for very first input that has been applied. Right? If you found the sluggishness of the instrument, say for example, it takes around 1 minute or say 2 minutes for settling down the temperature measurement of a say patient, and then immediately you apply some other element, some other input that is having some different temperature than that of the human body, you find that the reading will not be proper. So in this condition, we need to take into account the change the input, which are not static, but those are dynamic in behavior. The input is changing very rapidly, or say time which is smaller than the sluggishness of showing the output. Right. So since the input varies from instance to instance, it does the change into the output also, which is not a faithful representation of either of the signals. Maybe the signal during time interval 1, signal during time interval 2, and so on will not be faithfully represented at the display of your measurement system. So the behavior of the system under such condition is described by the dynamic response of the system. It's very obvious. Now this dynamic response is actually a combination of both, because of the inherent properties of the physical as well as the functional components into the measurement system, as well as the input that is going to vary, right? So combination of these two, the characteristics of the instrument under such condition is known as dynamic characteristics. I think now any doubt in understanding what is the meaning of dynamic characteristics and how it occurs into the measurement device or measurement system. So then once this is known, we need to identify what are the major properties we need to measure. So the dynamic characteristics refer to the case where the measured variable change rapidly. So variable, that is the input, is going to change rapidly. The sensors in the control system, this say you have to see this from different perspective. So till this point of time, we discussed only the examples where system is monitored. So for example, temperature of a water or the fluid into the beaker, the pressure, the instantaneous pressure of the air into the compressor. So these are the entities we have measured only for monitoring the system. But when we go for applying some control, say for example into the boiler drum, depending on the water level or the pressure inside the drum, we want to say make the system to have some corrective actions. So in that condition, the sensors in the control system we need to think of which do not react suddenly to the change in the input or the measured value immediately. So then it becomes very important to understand what are the properties of the measurement system that I am going to design for. So time required before measuring the instrument in the control system technology can indicate only the output based on the input received by the measuring instrument, and that is because of the signals accumulated during the time interval. So this is a total time interval t. Into this there is a t, for t1 time there is some value of signal, for t2 time there is some other value of signal, for t3 time other value of signal, and so on. So this summation, say, and the reaction of the control system will be based on the output that is shown by the measurement device, right? So the time depends on the resistance. See, again coming back to the element, the resistance, the capacitance, the mass, date time of the measuring instrument, and so on. The inherent properties of the physical as well as the functional blocks into the measurement system will be very influencing on the control achieved on the given process using this kind of measurement device, right? So there can be, say, the system can be studied by giving some kind of the known values, as we do in case of calibration. We have applied some known values of the inputs, right? So it is the very known value of the step input, ramp input, and so on of the measurement instrument is going to determine the dynamic characteristics of the measurement system, right? So dynamic characteristics of measurement system is defined by this very important step. Now you please try to understand this. In actual practice, it's very difficult to find out the very true input. So as discussed here, we are having t1 time some signal, t2 time some different signal, t3 time some another different signal, and so on. So it is very difficult to know which signal has influence in the display value of the output of the measurement system, right? So we, in the say standard test condition, we try to make the performance of this measurement system, that is the known value, we try to find it in laboratory first before applying that to the actual, say, measurement and the control process, right? So very important criteria into this is we must know the speed of response. This is the very first dynamic characteristics we must know, or we are, say, willing to find out. Any measurement system that I have devised for controlling of, say, some factors for boiler operation, which is dependent on the pressure inside the boiler, the amount of water level, the then temperature of the fluid, the temperature of the drum itself or the inside the drum itself. So these are variable factors. 5 or 6 number of factors are there. I must know how quickly the instrument is going to respond, right? So this is one that is found out, which corresponds to rapidity or quickness with which an instrument or measurement system is going to, say respond to the changes in the measured quantity. It's very, very important then. If suppose I know that the system is going to respond after 2 minutes, like in the case of your thermometer, then probably it will not be able to control any change, rapid change into the input if it is going to happen between 0 to 2 minutes. Because itself your temperature device, measurement device of the system, the thermometer is taking 2 minutes time to give the settle reading. Right. So I must have a very measured speed of response, the quickness, the maximum time it will take to have the settled reading. Right. So then it gives the way how quick it is going to respond, say how fast the sensor or say component of the measurement system reacts to the change in the input variable. Not only sensor here, though it is called a sensor, but all other functional element into the measurement system, like primary sensing element, from primary sensing element signal given to VC, VME and so on. So all the elements or components in the system taken together should have a very quick response to the change in the input, right? Then the response time becomes important. So the time required by the instrument or the measurement system to settle to its final steady state position after application of the input is going to speak about the response time. So ideally we want the speed of response should be a very higher. Response time should be also higher. Now there are some consequences of it. Let us discuss that. So response time generally, say again coming back to the example of the thermometer, say this is the input at 0 time. I am going to show one separate line here indicating this as a 0 time t, and then I have applied this to the temperature input. Say for example, thermometer applied to the human body, and then it is going to take some time to show the closeness to the reading, and then after a certain time it will become more or less stationary. So the instant it has started to give the linear, say, relationship with the output, the input, that is found out in terms of percentage. So what is said here, that it indicates the percentage time taken. So we can understand that, say this is time from 0 time interval t1 after t0. That is required to have the output displayed by the measurement system be very close to the true input, say between 90 to 99% of the input applied. So that is very rough estimation of the time response time for the measurement instrument, right? So the response time is, say, different for the different elements. Say for example, if the instrument is handy, that is a portable instrument that we are going to use, it is taken as say plus minus 0.3%. So when the instrument or the measurement system is going to display the output, say for example output with respect to the true input is within plus minus 0.3% of the value, the time taken will be, say, taken as a response time. There are different thumb rules. Okay, so I think this is just for information that it is taking 0.03 if the instrument is handy, and if it is a, say, with a switchboard type or where there is a instrument is having some pointer on it, so it will be taken as around 1% of the final full scale length. Now the delay time. So in the earlier diagram that I have shown, I have called this as T0. The input is applied. Now it won't start instantly at T0 to show some output, but it will take some time if you are able to visualize this. If I am going to show this output somewhere here, I am exaggerating. So the difference between the time at which signal is introduced and then it has started some change in the display device, we call this as delay time. It is exactly similar to the dead band in case of the static characteristics we have studied, right? So it is dead time, not delay time. So delay time is something when the 50% of the input is reached, suppose here, and the time. So if I call this as time 1, D1, then this is indicating D1, where it shows minimum 50% of the input value at the display. So length of the time taken to show the output so that 50% of the input is represented on the device, right? So this definition is very confirm about few kinds of the inputs. It may not be applied to all, because the input, if it is not possible to have a known value, will not be having the guess how and when it will have the 50% value reach. It is possible if I am applying sudden input here, the step input, because I know now the system true value suppose is 100 degrees Celsius. Now the thermometer going to catch up the time and show around 50 degrees Celsius. I will call that as a delay time, right? Then rise time, the length of the time it takes the output to reach 10 to 90%, say from 10% of the input to the 90% of input, when it takes the time here, I will call this as D2. So this is D2, rise time. So now why it is rise time? Because it is showing the increasing output displayed by the system. Say from 10% of the input to 90% of the input, if it is shown by the instrument, we call that as a rise time. So in output has been raised, it is rising, the output is rising. Then we go to the, I think date time I explained earlier. The time constant. Now, time constant is nothing but the time for the output to have minimum 63.2% of its maximum possible change. So for example, now 50%, now here is something called as a 63.3%. Now this is the time from T0. It is, I call this as a D3. So this is the D3. Say for, it is again very subjective. It is only clearly seen in case of the first order system. I think that will come across. So at this point of time, you understand that it's not possible to find the time constant for all the measurement devices or all the measurement systems, but very effectively is possible for few. So the wherever output is displaying minimum 63.2% of its input value, we call that as a time constant. So this definition also will vary depending on the requirement, right? Then the settling time, the time taken from the application of the input until the output has settled within the specific band of the final value. Now suppose the final value is settled here. Now it is almost parallel. The output shown in the red color is almost parallel, and which is very first instance, let us say, that is so going to show the constant line now. So then this interval will be, then I call this as a D4, that is the settling time. Now let me know any difficulty in understanding this, how we anticipate the response time for the instrument having the dynamic input. Please ask if there is some doubt. Okay, so if there is no question from you, then I think we'll move ahead. Date time I already have explained you. Date time is nothing but, say, as per this diagram, this indicates the date time. It is exactly similar to the date band, or sometimes equal to the threshold value that we studied in case of the static characteristics of the system. So I'm saying it is similar to date band. Why it is not called again as a date band? Because it is not the steady input, it is not the static characteristics, it is the dynamic characteristics that the system is going to respond with the time dependent change into the input value. So I think we'll move ahead. Now another important property, the third property we should say, is a measuring lag. So first we have seen the response time and the measurement of the delay that we have seen. let us see the third important property is a measuring lag. So from the definition, what we are seeing that the discussion, the instrument does not react to the change in the input immediately. The delay in the response of the instrument to change the measured quantity is known as measuring lag. So this is something we can say, assume similar to the threshold here. Now, in case of the static characteristics, what we have defined threshold as is the minimum input after which the instrument starts showing some display. We have taken example in case of the threshold, that is, you are moving with a two-wheeler, say starting from 0 speed to say 3 or 4 kilometers per hour. Your speedometer pointer will not show any deflection, but onwards it will start showing. So the moment it has started showing the deflection, we call that threshold. So same thing is going to happen because of the different components into the measurement system, say primary sensing element, VCE, VME, and so on. Either the functional or the real instrument, the physical elements into the instrument. Primary sensing element is sensing and giving signal to the variable conversion, then variable conversion is going to respond, going to give some output, and it is transferred to the display. So the time of applying the input here and getting some display at the instrument for dynamic response, I'm saying, for change in the signals with respect to time, we call that the measuring lag. Then the retardation delay in the response of the measurement system to change the measured quantity. So this is a retardation delay, right? So usually it is quite small. Say for example, the variable input. Another way I'm going to say apply the input change. Say for example, heating a water, heating some fluid into the beaker, and I have, say at room temperature, I have inserted the thermometer into it. Then first it will have transient response. What is the room temperature? Say suppose my thermometer is kept into the almirah and is having some lower temperature, say 3 degrees less than the ambient temperature. When I am going to dip that into the fluid, it will take some time to reach to the temperature of the fluid at the normal room condition. So then that is a transient response. Now once I am starting giving heat, I have started the burner then, and say some input is continuously added. Now with respect to now, it will be in sync with, say all the time the input applied and the set after settling the curve. Now if I am going to change the input, say for example input is changed, the thermometer will also try to show the similar output here, right? So this kind of matching will be there. The input and output will match. So this is something that is likely to happen, right? So the measuring lag, so there will be some lag that will be quite small, but it becomes highly important when the high speed measurements are required. So very quick measurements are to be taken, for example the process control. Then this is important. Say for example now some application like in the packaging industry or in some case of pick and place application, we have to handle something and the measurements are to be taken very precisely. That suppose now the application of packing 200 gram jars to fill, and then unless otherwise the weight of it measures 200 gram, till 200 gram the inlet valve will be open. As soon as the sensor gives the signal that 200 gram is over, it will stop the supply and then the bottle will move ahead. But between the time it is going to sense the true value of say 200 gram and the action taken, then there may be some measurement error. That error you want to reduce down. If suppose that error is 1%, then actually you are going to incur a huge loss. That you are filling actually 1% more item over the 200 grams. So it will be more around 2-3 grams more into the particular packaging. So there are various cases, various systems in which precise measurement become very important. Right. So it is quite small, but in the small lag is going to become highly important when the high speed measurements are required, because then that will not correspond to the very true status. And say I give an example. If in case of commerce, if it's going to happen, you are going to give some more quantity than the 200 grams to the customers, whereas you are getting paid for 200 gram only. So in proportion that you can assume, you can imagine, depending on your sales, your loss can be say multiple folds, right? So the high-speed measurement system, as in the dynamic measurements, it becomes essential that the time lag should be reduced to the minimum. So this is very important. That's what he's saying. The measurement lag. Why measurement lag is important to find out in case of the measurement devices, right? So the measurement lags are of different types. Say basically a very broad classification, which is retardation type, and the next one is the time delay. So in the retardation type, the measuring lag response begins immediately after the change in the measured quantities occurred. Okay. Then in case of the time delay, the measuring lag, the response of the measurement system begins after a dead zone. After a dead zone, after the application of the input. Right. So I think this will come across at some other place again. We'll discuss this when we'll go for the characteristic measurement. But at this point of time, you say that you keep in mind that the measurement lag is broadly classified into retardation type and time delay. So let us come to the fourth important property, that is called the fidelity. Now, if I go back to the earlier example, say for example the output and the input, it is not it is output and the input both with respect to time. I will call this as the input and this is the time. Say input I am showing with blue color. Say for example I am going to apply the input here. Input is changing with respect to time, and the time taken by the instrument over the time, say to capture this, something like this, coming closer to that. Now you see, for the interval of the time, the response going to become will give some different behavior, right? So in such condition, the ability of the system to reproduce the output. My input is say with blue color, output is shown by some different color now. Now how closeness or how the input is reproduced at the display of the device or the measurement system. Ideally, we want same. So it's very obvious that any one of us, if we want to design an instrument, will want that output and input should overlap, should be the same. But in actual practice, the instrument is not going to be in that fashion. So the degree to which measurement system indicate the changes in the measured quantity without any dynamic error will be then called as a fidelity. If the error is removed or if the error is neglected, then what is the degree with which the output is say mapped with the given input is nothing but the fidelity. So this is a statement definition. Then if a linearly varying quantity, say just now I take an example, if a linear varying quantity is applied to the system and if the output is also linearly varying quantity, then system is set to 100% fidelity. It's very obvious that the blue line and red line are going overlapped or moving very close and parallel to each other. Then we say that the fidelity is 100%. Though ideally, that's what we said, it should be 100% fidelity. That output should match very closely or exactly to the input. It's very ideal. Also, the output should appear in the same form. It's very important. Now, this is another aspect of the say dynamic characteristics. Sorry, in the same form. Say the form should not change. The deviation. Suppose now output is shown with red color. It is showing some deviation in the output. It is not the same form. What is the form here? Linear form is given for input, but at the output is not linear. In the static characteristic, we found non-linearity, but that was because of the say readings with a different constant input applied. Now here input is constantly changing. Now what is the difference between the curve? Into that it was say input here into the static characteristics and output was here, and we are given the line. Now in this case input output correspond to y-axis, and on the say x-axis there is a time as an important variable into this dynamic system or dynamic characteristics. So the same curve we are applying with respect to time now, right? So there is no distortion produced in the signal by the system. Now this is something distortion. I am giving linear input, and because of the variable conversion element, suppose there is a, I think we have discussed that in case of filtering, and there was one particular word where we have found that the signals for 50% input are linearly magnified, onwards it is not. What is that word? Anybody able to recall? Just in the previous lectures, previous last to last lecture, we have studied this. It was filtering, and some more word was there. So if the amplifier is going to work in that fashion, we find that the signal will be changed, right? So this is assumed that there is no distortion because of any of the functional part, like say variable conversion, variable manipulation, and other places wherever amplifier and other devices are used. Those are not going to distort the signal received at the input of that particular phase, right? So ideally it should have these elements into it. But that is why we are finding the fidelity that is not following ideal relationship, right? So in the definition of the fidelity, any time lag or phase difference between the output and the input is not included. This is what is a very important assumption. It's not very practically, but it's assumed that the time lag or phase difference between the output and the input is not included. If we include that, then definitely it is very difficult to find out a fidelity, right? I think this also will be discussing when we'll go for the second order system and with say sinusoidal input and like that this also will come across, right? Any difficulty in understanding, let me know, otherwise we'll move ahead. I think we'll take one more slide and stop here or two. So this is the fourth important dynamic characteristics of the instrument. No response from you. Okay, let's assume you understood everything. Let us go to the next one. The fifth important characteristic is the dynamic characteristics. So this I think is the last slide we are going to study on the today's class. Now coming back to the earlier example, just now we have discussed that the input with respect to time is applied, and that is going to say take some time to reach the matching between say input and this is the output. Now it's very simple. Dynamic error at any given interval of time will be the difference between the input and the output shown. It's very true as that of the accuracy that we study in case of the static characteristics, right? Or the precision that we are studying, or the precision and the accuracy that we are studying in case of the static characteristics is similar to the dynamic error. But again, it is different here. It was input versus output relationship in our static characteristics. It is in with real time. So the difference between the true value of the quantity changing with time and the value indicated by the measurement device or measurement system will be the dynamic error. Now it is assumed that there is no static error present into the instrument. We can understand the complexity. It is assumed that there is no static error. Now if suppose there is a static error, take example of the system, say micrometer screw gauge. We have found that micrometer screw gauge is having accuracy of the error, static error of say plus minus 0.01 millimeter into it, and then that is used for measurement of the variable input, maybe varying slowly. So the dynamic error, the total error given by the instrument, or the difference between the true input and the output shown by the instrument if the input is varying. will be combination of the static plus dynamic error. You try to understand. The error shown in the after the measurement, may it be the static property measurement or the dynamic characteristic measurement, the error will be found at the display of the instrument. The true input I am knowing and the display is known. I cannot quantify what is the percentage or contribution of the static error into it and what is the contribution of the dynamic error. How much part of that error, total error shown, is out because of the static error and the remaining, or what is the proportion because of dynamic error, is not known. And that is why it is very difficult. Now you can understand, it is becoming more and more difficult to know the characteristics of the instrument in the dynamic response. And that is why we assume here that the static error is removed. The instrument is well calibrated and the static error is removed, or it is not present at all. Which is very, very practically impossible, because we have gone through the systematic error sources, the random error sources and the miscellaneous error sources. And we also have seen that randomness and the miscellaneous errors are very impossible to remove. So then that component will always be there in dynamic error. But now in this case, the time period is so small for the measurement, the interval time of the measurement is so small that the static errors are not going to affect more. So again, this is an assumption. Exactly, we don't know what is going to happen, but that's what is assumed, that there is no static error present in the instrument. Okay, so I think I will stop here for today. I think we'll discuss again from the next class. Now let me know any doubt. Right. So I think I will remind you that we are going to have tests tomorrow at 12 o'clock. So that will be test number 4. Now let me know on which topic you would like to have the test. Shall it be on the drift and the sensitivity drift calculation, or you want to have that on the uncertainty propagation? So I am planning that for uncertainty propagation that we have studied in the recent lectures. There are few numericals you can take help of, or you can go through the numericals and try to get those clearly understood. So into these Google Forms, you will have to give the answers, as well as you have to submit the solutions that you have made in the form of the PDF file. So once you submit the Google form, immediately you load the what you can call the answers that you have calculated on your respective practical groups.
Sir,
Yes, go ahead, please.
sir, regarding the first 3 class tests, can you share us the solutions?
No. Why you want the solution?
Sir, we just want to know if we did it correctly or not.
I cannot give any commitment right now on this one, but we'll definitely think on.
Sir, or can you discuss the procedure?
Okay, I will discuss the process. Yeah, that can be done. Definitely, that will be done. No issue.
Thank you,
So I
sir.
think we'll stop here for today. I will take care of that. We will discuss that definitely. Right. So thank you for joining. We'll stop here for today.